Now we're going to deal with two basic sampling distributions. One is going to be dealing with the mean, mu. That's the one we're going to talk about first. And the other is going to deal with proportions, p. So when we have quantitative data, the sampling distribution of the different statistics will be the probability distribution for all the different possible values that statistic can take when it has a sample size n. Now, when we're trying to estimate the population mean mu, we're going to use x bar, which stands for the sample mean. The sample size for that's going to be n, and the population standard deviation is going to be sigma. Now the sampling distribution for x bar, it's going to have its own mean and standard deviation. Now the expected value that x bar should take should be the population mean mu. We do take enough samples of whatever size we're determining it to be. The average of those samples should come out to be the actual population mean. So it's no surprise that the mean of x bar, and this is the notation for it, mu of x bar, is going to equal the actual population mean mu. Less intuitive is the standard deviation. Sigma x bar, so the standard deviation of the sampling distribution x bar, is going to be the population standard deviation divided by the square root of n. This is often called the standard error of the mean. Now, if x is normally distributed, then the distribution of x bar will also be normally distributed. We run into a problem if we're taking a value for x bar that is not from a normal distribution, however. So here's an example. So distribution of a fair die. So the different possible values for rolling a single die are 1, 2, 3, 4, 5, and 6, and they have a uniform distribution as far as what is possible. Now it's not strictly uniform because it is a discrete distribution, but all the probabilities will be the same. So calculating these things out using the methods of chapter 3, we'll find the mean of the die to be 3.5 and the standard deviation to be 1.708. This is not a normal distribution. It's not mound-shaped. It is symmetrical, but it's not mound-shaped. So what do we do when we deal with something that doesn't have a normal distribution? Well, if we take an estimate, and we're going to take 200 simple random samples of size n equals 4. We're going to calculate the sample mean for each of these 200 samples. We're going to repeat for sample sizes of values 10 and 30 to show how n is changing the look of the distribution. In the next few slides I've got those distributions. So the first one at n equals 4. Clearly it is mound shaped. We have a little bit of symmetry, but it doesn't appear to be normally distributed. We've got some issues on both sides, in fact. N equals 10, it's getting a little closer. There's less in the extreme areas and much more in the middle. Certainly getting better, not exactly normal. When n reaches 30, however, if you look, it's almost perfectly symmetrical. Yes, these two things are a little off and these are a little off and so forth, but our distribution very much resembles a normal distribution. And typically the magic number when it comes to this is 30 for these sample means. So typically if we take an n value of 30 or more, it doesn't matter what distribution we pull it from, x bar should also be approximately normal. And that leads us to the central limit theorem. So it becomes approximately normal, the shape of that distribution becomes approximately normal as the n value increases. It doesn't matter what the shape of the population was, provided that n is sufficiently large. Again, typically we're going to use the value of 30 when dealing with a sample mean.